First, before we tend to write the subroutine, we need to know all about the input files of this simulation. The first input file creates the axis symmetric model, and you could open it in the graphical user interface of Abaqus. Note that the required keyword commands must be written in the other input files. Now let's explain the first input file. After the star heading command, the second line indicates our model's name. The next line is the star preprint command, and after that the nodes are defined. As you see, the first variable determines the node number, and the next two indicates the node's x and y coordinate respectively. Note that we only have two coordinate components because our model is axis symmetric. Next, the elements are created with the star element command. To refresh your memory, we use three different elements. One of them is CGAX4. This one has 4 nodes. The first number indicates the element number, and the other 4 are the element node number. The next element is the CGAX3. This one has 3 nodes. The first number is the element number, and the others are the node number. The following lines create node and a node set. In line 144, we defined an EL set. The next line determines the first element number, last element number, and the interval between the elements' numbers respectively. In line 147, an EL set is created with this name, and all its elements' numbers are given here. Lines 150 to 152 indicates that we created a solid section with the rubber material and cross-section of 1. Again, another EL set is created and its elements' number are determined. The next part is built to 1. As before, we have the nodes numbers and their coordinates, the element definition with the type SFMGAX1, and the elements numbers and their connected nodes. Therefore, we defined the nAdapt set. The following lines indicate the half of the nodes numbers determined with the variable JSL nodes in the PowerPoint. They are the nodes of the one side of the tire positioned on top of the tread. Node set nAdapt LAGR includes nodes of the bottom of the tread. The node set rim includes node number 80. The next node set is rim node, which indicates node 3 and 4. The next two node sets are sim and QA test sim, and their nodes numbers are determined here. In line 314, the tread element set is created. Two EL sets are generated by the names middle tread and QA test tread, including elements number 39 to 50. With the interval 1 between their numbers. Side tread EL set is generated containing the elements number 14 to 28 with interval 1. Also inside S2 and inside S4 a EL set are created, and their elements numbers are determined here. In line 327, we created a surface including some elements. In the next two lines, the first variable inside S2 and inside S4 indicate the element set that create the surface. The other two variables S2 and S4 determine which element faces or edges must be selected for the surface. You can find more information about these so-called face identifiers in the Abaqus documentation. Next, we define some materials. The first one is named belt. Here we have density elastic and hyperelastic properties in the form of Marlowe, and we put the stress and strain data for the hyperelastic. Another material named carcass is defined with the same material behavior. The rubber material has density hyperelastic with long-term moduli and viscoelastic with the Prony domain time. You can find more about the last two material behaviors and their variables and values in the Abaqus documentation. Next, we defined a step named inflation, and the nonlinear geometry option is on. Line 436 indicates that our step is static. The following line determines the initial time increment, time period, minimum time increment, and maximum time increment respectively. Finally, in the last line, the step is ended. Before we explain the second input file that creates a 3D model from an axisymmetric model, we present some notes about symmetric model generation command that can execute the mentioned modeling. These 3 points create the cross-section of the axisymmetric model, which is going to be revolved. The following 4 lines define the theta revolution value. Our 4 lines create a 360 degrees revolution of the axisymmetric model. Now you can see the symmetric model in this picture and the surface the tire rolls over. Created with the commands we have just discussed here. Now let's attend to the second input file. The file can model the tire from axisymmetric to a half 3D model. Lines 2 to 9 are just some descriptions about the file and don't do anything. Next, we have the star restart command for saving data. The following line creates a node containing node number 9999 and its coordinates. In line 13, we have the star symmetric model generation command, which is explained before in PowerPoint. In line 27, we define a rigid body. It is defined by the S-road surface created in the previous lines, and its reference node is named road. In the following line, we defined a contact pair, and the interaction property is named S-rigid. Next, we define the static step with the long-term parameter. Line 77 indicates the initial increment and time period respectively. In line 78, we have boundary conditions. With the OP equal new parameter, all previous boundary conditions will be deleted and new ones are defined in the following lines. The degrees of freedom from 1 to 6 of the node sets, rim and road, will be 0. Also, the degrees of freedom 1 and 2 of the node sets, SYM1 is 0. In line 82, all loads will be deleted by the parameter OP equal new, and in the following line, the new pressure load is applied on the inside node set with the magnitude of 200,000 pascals. In line 84, we requested outputs for the node set road with the star node print command. The outputs are displacements and reaction force. Next, we have the star EL print command. In line 88, we requested field output for each increment. In lines 89 and 90, we requested output for the element stress and logarithmic strain. Also, the same outputs are requested for the rebar element. In lines 93 and 94, the displacement output is requested for the node. Next line, the contact output is requested with default variables. The following line requested history output for each increment with default variables. In lines 97 and 98, some outputs are requested for the node set road, displacement, reaction force, and constraint force. In line 99, the step ends. In the second step, we have displacement control. In this step, we defined the displacement with value 0.02 for the node set road in the degree of freedom 3. In the third step, the initial increment is different from the previous step. Also, we have the load control here. Lines 122 and 123 imply that we deleted all loads and apply a concentrated force on the node set road in direction U3. with the magnitude of 1650 Newton. Now let's offer some starting points for the third input file. Here we explain how to transform the half 3D tire model into a whole one. With the star symmetric model generation reflect equal line command, we would be able to reflect a partial 3D model through a symmetry line to make a whole 3D model. Now let's attend to the third input file. As before, after the star heading command, we have the file descriptions from lines 2 to 6. In line 7, we have the star restart command with frequency 100 that saves the results for every 100 increments. Next, the star symmetric model generation command, which we talked about it in the PowerPoint. In line 10, the star symmetric results transfer command is defined to transfer the results from previous model, which is in step 3, to this model. Next, we defined the step with 100 increments and the nonlinear geometry is on, because we have contacts and nonlinear material properties. In line 14, we define the static step with the long-term parameter and the incrementation type is direct. The following line indicates the increment size and time period, respectively. Next, we define boundary conditions and renewed the boundaries with the OP equal new parameter. For example, the degrees of freedom from 1 to 6 of the node set rim are 0. Lines 20 and 21 imply that for the node set inside, the new pressure load is applied with the amount of 200,000 Pascal. The next two lines are indicated that the concentrated force in the direction U3 is applied on the node set road with the magnitude of 3,300 Newton. In line 24, we have the star node print command for the node set road with the frequency 1. The requested outputs are displacement and reaction force. Next, the star EL print command with the frequency 0 is applied. The field output is requested in the following lines for the element and rebar element, including stress and logarithmic strain. Also in lines 33 and 34, the displacement output is requested for nodes. In line 35, the history output for each increment is requested with default variables. The following lines indicate that the displacement, reaction force, and concentrated force output for the node sets, road, and rim are requested. The next input file is about to simulate the whole model in the steady state step. After the star heading command, we have the files description from lines 2 to 5.